Hey, students of Seneca, thanks for joining for our second live stream. Today, by popular demand, we're going to be going over some predicted questions for GCSE Physics Paper 1. I hope the chemistry one yesterday was useful. Thanks for all your feedback. Some people gave us some really handy tips about improving the quality. I might be sneaking my duvet into work tomorrow because that should help with the sound quality. And again, apologies for, we're a startup, champagne taste on a lemonade budget. But they're hopefully just going to get better if you guys find these useful. So without further ado, let's dive in. The plan for today's stream is to go over some of the Seneca predicted papers for GCSE Physics. I've tried to pick topics that were requested and popular. So we're going over, energy was quite requested. So we'll be going over specific latent heat and the differences between that and specific heat capacity, which is really good fodder for exams. We're also going to go over renewable energy because that's quite contextual at the moment. So I think it would be I think potentially one, interesting to go over, and two, potential exam question, who knows. And then finally, we're going to do radioactive decay, which is super requested. So hopefully we'll clear things up, go over some equations, and get you feeling really confident for the exam tomorrow. How is everyone feeling? Hey, everybody. I'm going to do a better job at the chat today as well. Yesterday, there were a few issues. So yes, I know I'm a little bit late, sorry. But I had to make my cup of tea before coming into the lesson. Otherwise, it wouldn't have been fun for anyone. Okay, so I'll start sharing my screen and then we'll get into it. Any questions you have, give me a little shout. I've got my phone open so I can see the chat, because when I share my screen, I lose the chat, which is annoying. And okay, so let me get into the sharing mode. So share screen. And we are going over some nice past papers. So I've tried to pick 3 questions I thought would be quite high yield, as in like they would be really useful topics that come up a lot in exams. So hopefully that will get you nice and prepared. So let's dive in. Like I said, we're starting with latent heat. So this is one of the Seneca predicted papers that we're going to be going over. And it should, some of the predicted papers we've had so far have been quite representative of what's come up. So hopefully it will be useful and get you ready. So first question, what is the equation for specific latent heat? So this is an important one to remember. Specific latent heat is equal to the mass times by the latent heat energy. Key things to remember, the mass has got to be in kilograms. They always do it where they will give you they'll do they'll give you like the measurement in grams, and you'll have to convert to kilograms, and to convert from grams to kilograms, divide by 1,000, something that they love doing. So always remember, for specific latent heat, you've got to keep that mass in kilograms. So what does specific latent heat represent? Well, specific latent heat is the amount of energy required to change the state of 1 kg of substance without changing its temperature. And I'd say that's probably the key difference between latent heat and specific heat capacity, which is really important to remember, because they'll often get you to differentiate between them in the exam. In specific heat capacity, we are increasing the temperature. Specific heat capacity is the energy required to increase the temperature of 1 kg of substance by 1 degree Celsius. So temperature is going up. Latent heat, the temperature is not changing, the state is changing. And when the state is changing, the reason the temperature doesn't go up is because the bonds are breaking, because when we change state, bonds break. That's something that might come up in like a 7 to 9 stretch question. So that's what's happening during a state change. The bonds between the molecules or atoms are being broken. Okay, so there are 2 types of specific latent heat you need for your exam. You know what? Anyone type in the chat and let me know what we need to be looking for. Yeah, so Very good, very good. So we've got fusion and vaporization. Okay, and fusion, that's just a posh way of saying melting. Fusion, it's like melting from a solid to a liquid. Vaporization, that's just a posh way of saying boiling. So think about vapor, it's a gas. So we're going from a water vapor. We're going to a vapor from a liquid. Okay, so those are the two that you need to remember. Okay, what is the standard unit for energy? So how do we measure energy? Physics is big on units. We need to make sure that we are familiar with all of them. For energy, it's all in joules. Okay, so that's how energy is measured. They might get you to convert from joules to kilojoules. And again, just like grams to kilograms, to go from joules to kilojoules, you divide by 1,000. Okay, so this is a really common thing that comes up in exam papers. They will give you a list of different values. So we've got specific latent heat diffusion, specific latent heat vaporization, and specific heat capacity. And then they'll get you to do some kind of calculation. It's up to you to pick which value you need to use. So given that most of this question is about latent heat, you would probably be thinking, I'm probably not going to need specific heat capacity. That's probably there to confuse you. And again, use the units to help you. Latent heat are always in joules per kg, where specific heat capacity will be joules per kg per K or per degree C. K is Kelvin, another way of measuring temperature, whereas degree C, Celsius, probably familiar with it. So given that a liquid is at 100 degrees Celsius, that's the boiling point, how many joules of energy would be required for 500 grams of the liquid of the gas to change state? Well, before we get too ahead of ourselves, we've got to think, okay, what does the question want from me? So I know we're going from a liquid to a gas. So that sounds like it's going to be some vaporization up in here. So we're going to be needing that 2.2 times 10 to the 6 joules per kg value. And don't be afraid that there are other values on the page that you're not using or you don't need to use, because they're probably there intentionally. They're trying to trick you out because examiners can be mean. Okay, so always this worked example is a really good way to structure your answer. Always start by writing the equation you're going to need, because if you write out the equation, sometimes you can get a mark just for writing out the equation you need to use. So that's a good tip to remember. And also, it's so easy in the heat of an exam to make a silly mistake and accidentally divide rather than multiply or something like that. So just make sure, write out that equation again. 1, you could get a mark for it, great. 2, it'll make sure you are doing the right calculations. Now, we're told that there are 500 grams of liquid. Now, what do we need to do to that 500 grams of liquid? I'll have a little look. Tell me, what do I need to do? Let me know on the chat. So, yes, exactly. We've got to convert it into kgs. So 500 grams to kgs is when we're going to divide by 1,000. So it's going to go to 0.5 kgs. Now, we already know which value we need to use. We need to use that specific latent heat of vaporization, because we're going from a liquid to a gas. So it's going to be 2.2. Bam. Okay, 0.5 times 2.2. Not too bad math. Hopefully my mental math won't let me down, but I think it's 1.1. Boom. So 1.1 times 10 to the 6 joules. Okay, what's the effect on the substance's total mass when it changes state? So I would say, as a general rule of thumb with these kinds of questions, always stick with laws of conservation. So mass is always conserved and energy is always conserved. So if you're in an exam and you're a bit stuck and it's what's going to happen to the energy? 9 times out of 10, the answer is probably going to be conserved. So it's a good little backup to fall back on. So that brings us to the end of the first predicted paper question we're going to go through, and we're ending with one of our stranger gifts, but I kind of like it. But key things I would take away from this: always remember your units. It's such a simple thing, but it's really easy to forget in the heat of the exam. So make sure you're working in the right units, particularly with latent heat. It's always going to be in kilojoules. So make sure you convert that gram number that they give you into kilojoules. Okay, how did everybody find that? Do we have any questions on specific latent heat or specific heat capacity? I might disappear for a moment while I check the chat. Any questions? The gifts are a group effort, just so everybody knows. I realize the screen's gone, but I'll be back. Okay, so that is the first question done that we're going to go through. Next, we are going to be going over renewable energy. And I thought this would be a good question to go over because, one, it's been very contextual at the moment in the news. There's been lots of protests about reducing our energy consumption and using renewable resources. So it's quite contextual and hopefully interesting. And it's also just important for the world in general. So it's good not just for your GCSE physics exam, but good to know about anyway. And with renewable energy, there's a lot of keywords and a lot of buzzwords you need to use in your answers if you want to get those marks, okay? A lot of the mark schemes have underlined words that you have to use in order to get the marks. So it's really important to be specific with your scientific language. So which of the following are sources of non-renewable energy sources? Well, if we're talking about non-renewable energy resources are ones that can't be reused. So we have our cute little list here. Which of these cannot be reused? So we can't reuse nuclear because once nuclear decay has happened, it's not going to happen again. That was a little preview for the radioactive decay question we'll be going over a little bit later. Geothermal, that's going to be renewable. That's heat from volcanoes like underground. It's going to warm that water. The water's going to boil and drive that turbine around. Biofuel, I mean, it's got bio in the name, so it's made from crops. Crops can be regrown. Water everywhere. That's a good renewable energy source. Coal, nope. Oil, nope. They're in the same kind of ballpark. So those are the non-renewable ones you need to be aware of. Other things include like natural gas. That's a non-renewable energy resource. Okay, so now we're going to get into a little bit of a calculation and like more ethical question, which do come up in physics, so they are important. And a lot of the time with these kinds of questions, you're going to be faced with like a massive big chunk of text, and it can be quite overwhelming. So my tip would be make sure you break down the text into more manageable chunks. And you could do this by underlining or whatever works for you. What I like to do, I like to circle the keywords, and then normally like next to it in the margin or like just underneath, I'll write out the key figures that are given in the text. And that gives you a really quick reference where you can go back and be like, okay, these are the figures I need for the calculation. So if the average electricity consumption of a family was spread out over the whole day, it would require 2 kilowatts of power continuously averaged out over winter and summer. Their annual electricity bill is £1,200. Okay, I was going to say £12,000. That would be a big energy bill. So in that circumstance, I would probably circle the 2 kilowatts of power continuously and the £1,200 pounds, and then I would write 2 kilowatts of power per day? Yes, 2 kilowatts of power per day, and then I put annual bill £1,200, because then I've got a really nice quick reference of the key facts and figures that I'll need. And then a house has 12 solar panels fitted to its roof, and its energy is needed throughout the year. Each panel can produce 150 watts when it's operating at its maximum efficiency and costs £200. So again, here underneath I would write 12 solar panels, each 150 watts per panel and £200 per panel, because then I know those are the key facts that I'm probably going to be needing later. Okay, discuss the advantages and disadvantages of fitting these panels to the roof. So this is a 6-marker question, so it's a bit of a beast. And what you need to do with these questions is structure your answer really clearly to make it really easy for that examiner to give you those marks, okay? So we'll start with advantages, and you could either have a little heading or you could have a topic sentence on there are several advantages to having solar panels. So then you know we're talking about the advantages first. Clue, if it's 6 marks and it's asking for advantages and disadvantages, it probably wants 3 of each. So don't give like 5 advantages and 1 disadvantage, try and keep it even. And also if they're giving you a bunch of figures and it's a 6-marker, they probably want some kind of calculation in there. So use the information you're given to help guide your answer. So advantages of using solar panels. So they won't produce any CO2 or what? What else would they produce? What can you think that's related to the environment, pollution? So I would say greenhouse gases, because that is what, all pollutants, either is fine, but yes, they won't produce any other pollutants. They're also a renewable energy resource, so they can be used again. So beneficial to the environment. So again, those are examples of good keywords you want to be using in these kinds of questions. You want to be using words like renewable, you want to be using pollutants, greenhouse gases. Those are the kind of words that are going to get you those marks, okay? They provide a stable source of power, since power blank will not affect the household. Well, power cuts will not affect the household. Not that they're particularly common in the UK, but I grew up in Zimbabwe and there were power cuts all the time. So a lot of my revision used to be by candlelight. So the solar panels will reduce the electricity bill of the household. So that's the main reason why we would get these, to reduce the bills. And the family can also potentially sell energy back to the national grid. The national grid is the national electricity supplier. Any electricity they use will also be free. They won't have to pay for it. Once you've paid for the solar panels, boom, you're getting that free energy. Okay, disadvantages. So again, once you've listed out the advantages, just have another sentence very clearly stating that you're now going to be talking about the disadvantages. So something like, however, there are some disadvantages of using solar panels. So the solar panels may not produce all of the energy that the family requires. And this is especially likely during the winter season. So that makes sense, right? It's colder, it's not as sunny, and like winter's awful, like it's dark by 4 p.m. and it's cold, and like then you get home and you haven't got any electricity. Like, I would not be about that life. The family would need to purchase a lot of solar panels in order to pay their whole bill, and the initial cost of the solar panels would be very substantial. So the setup cost is very substantial for a lot of renewable energy resources, not just solar panels. The power generated is not stable, since there is a variable output based on the weather, the time of the day, and the season. Okay, so that is that is some good things to remember about renewable energy and the disadvantages. Okay, so as promised, next we're going to get onto these calculations. Okay, so calculation questions, I'd say the key thing I would remember with calculation questions is make it very clear how you're structuring your answer. And that's not just for the examiner, but also for you, because then it can just make it a little bit easier to see what you need to do and all that kind of stuff. So with renewable energy, the key kind of calculation is going to be payback time. And that's the amount of time it takes back to get back the money you initially spent. So do you remember how many solar panels there were? Can you type it out? Like in the exam, you could just scroll up, but it's fun to be interactive. So I would say that there were 12 solar panels. Now, how are we going to do this calculation? So we know that there are 12 solar panels, and how much energy did each solar panel produce? Well, in the exam, we would hopefully have our nice little table with all our key little figures next to it, and we know it's 150 watts. So 12 times 150 is going to be 1800. But if we have a look, always check the units. They want it in kilowatts. So to go from 1800 watts, we divide by 1,000 to get 1.8 kilowatts. And that's not enough energy on average. Why not? Because the family used 2 kilowatts per day, they need 2 kilowatts per day. So if the solar panels are only producing 1.8 kilowatts, they're still going to be needing to get some energy from the national grid. So 12 solar panels, how much are they going to cost? Well, we've got £200 is how much one costs, and there are 12. So it's going to be £2,400. So if the electricity was supplied in total by the solar panels, how long would it take the family to pay back the initial setup cost? Well, again, this is where we use the numbers to help us. So we see their annual bill is £1,200. So if it costs £2,400 to get the solar panels, but you're saving £1,200 a year because you're not having to buy electricity, boom, we've got some quick math. 2,400 divided by 1,200, that is going to be 2 years, okay? But in reality, it's going to take a bit longer because we're only getting 1.8 kilowatts from those 12 solar panels, okay? So there we go. That is a quick run through renewable energy and the key terms that you need to remember for your exam. Key takeaways from this question, I would say, remember to structure your working out really clearly. Always write the equation you're using at the top, just like in the last one. And I would also say keep your long answers well structured too. It's just like a calculation, but with words. So make it very clear that you're talking about advantages, then disadvantages, all that kind of stuff. Okay, so next we're going on to radioactive decay. Okay, so this was one of the most requested topics for the paper. So this is the next predicted question we're going to go through. And radioactive decay comes up quite a lot, and it's often quite good fodder for like 7 to 9 questions. So they can get a little bit lively, but all in all, they're pretty good. So radon 2219, radon, did I say that right? Radon 219 is radioactive. It may be represented by 21986Ra. So any of you that did chemistry, hopefully you'll remember what those numbers mean. And the big number, that is what we know, what we call the mass number, okay? So the mass number, who knows what the mass number does or like tells us about a compound? What does the mass number do? So the mass number, that's the total amount of protons and neutrons, okay? So that is what the big mass number tells us. Oh, and the smaller number, that is what is that number? Awesome, that's the atomic number or proton number, and that tells us the amount of protons. Okay, so if we have a radon 219 atom, how do we work out the number of protons and neutrons? Protons is easy, that's just the mass number, so it's going to be 86. And the number of neutrons, that is just going to be 219 minus 816, which I think is at 133. Boom, my mental math didn't fail me. Amazing. So that's how to work out the number of neutrons. You just take the mass number and you subtract the atomic number, which is important. It's an important calculation to remember. And it's kind of like on the overlap between physics and chemistry. So 219 will decay with the emission of an alpha particle. So what makes up an alpha particle? This is one of the 4 types of radiation you need to know for the physics exam. What are the other 3? Do we know? Sound off below. Let me know in the chat. What are they? We've got beta, which is an electron, neutron, which is a neutron, and then gamma, which is a wave, okay? So the components of an alpha particle, alpha is the biggest particle, and it's 2 protons and 2 neutrons, okay? And that is what we call a helium nucleus, because helium has 2 protons and 2 neutrons, and the nucleus of an atom is just the middle without the electrons. So if you see an alpha particle called the helium nucleus, boom, 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 that's why. Okay, so equations for radioactive decay. These are definitely on the harder end of the spectrum for GCSE physics, and will be in the 7 to 9 range. But there are some tips which can always help you identify what you need to do to get the right equation. So because it's alpha decay, that means we're producing an alpha particle. So the first thing I would say is that alpha particle or the helium nucleus has always got to be on the product side of the equation. So straight away, I know it can't be that middle equation or like middle, like second one. It's not quite the middle because that's 4, but you get me. So we know it can't be that one because we're adding an alpha particle. We're producing an alpha particle because it's alpha decay. Next thing, the numbers have got to add up. So the numbers along the top on the reactant side have to add up to the numbers on the top on the product side. So this one, 217 plus 4, that equals 221, not 219. So I know that top equation is wrong, okay? Then if we go down here, we have 215 and we have 4. I like that so far. That adds up to 219. But we've also got to check the bottom, which is the atomic number. 82 plus 2, that's 84. So I know it can't be that equation. So I know it's got to be the bottom one, but I'll tell you why. It's because, boom, that top number, 215 and 4, 219. And on the bottom, 84 and 2, 86. So again, we're coming back to that concept of conservation. Mass is conserved. So that law of conservation of mass means that the mass number and proton number, they've got to add up to be the same, both sides of the equation. We can't just like lose a neutron. It's not going to disappear. There's no like atomic Houdini that can make atoms and like neutrons disappear. They've got to be on the left and the right of the equation. Okay, so now we're going to talk about another thing that comes up a lot. We talk about the half-life of radioactive substances. So this comes up quite a lot. And radon has a half-life of 4 seconds. So what is meant by the half-life? Well, the clue is in the name. So it means that every 4 seconds, the activity is going to decrease by half, okay? So that is what a half-life means. At the start of an experiment using radium-229, the count rate was measured with a counter. What kind of counter measures radiation? It's a Geiger counter. And that is how we measure radiation. Oh,
hello, students.
Oh my God, Richard is back
again.
Thank you very much.
I brought Jono a cup of coffee because I thought he's doing such a good job.
Oh, you're so sweet.
What's what.
Thank you.
How's it going in here?
Yeah, not too bad. Enjoying it. Doing some nice GCSE physics predicted.
Nice. Top tip for
questions.
Physics.
Ooh.
Do you want to hear it? Top tip for physics is make sure when you're substituting a number into an equation or formula, make sure the units are right. You heard it here first.
Top tip from Richard, physics guru. Thanks, Richard. I'll see you in a bit.
Enjoy.
Thanks. There we go. Nice surprise visit from Richard. I've now got a nice little cup of coffee. Although I'm going to be sleeping tonight if I have coffee, but I feel rude not drinking it. But I'll go for a run after this and to discharge all the caffeine. Okay, so where were we at? We're talking about half-lives. Okay? That is the time it takes for the activity of a substance to decay by half. Okay. I wonder what my half-life is for energy in these videos. I hope it's a high half-life. And we measure activity using a Geiger counter. Okay. So that is how we measure radiation. Loving the comments about Richard, by the way. That is how we measure radiation with a Geiger counter. So we're told that, again, when we have tons of numbers, remember, just write out the numbers next to the text, so it's not so overwhelming when you go back and look at it. So we say that the radon 219 has got 1600 counts per minute. How long will it take the count to decrease to 500 counts per minute? We're ignoring radiation in the background. That's an important thing to remember because there's always little bits of radiation. It could come from like cosmic rays. Some like rocks are radioactive. So radioactivity is everywhere. So the way I like to do these questions, I am a visual learner, so I like to draw stuff out. It makes me feel safe. So I would draw 1600 to 8000, so that's one half-life. 8000 to 4000, that's another half-life. 4000 to 2000, that's another half-life. You see where I'm going with this, right? 2000 to 1000, that's another one, and then 1000 to 500. So that is 5 half-lives. That's always the first step in a half-life problem. Always just count up the amount of half-lives, and I just draw out the numbers with cute little arrows and then count up how many arrows there are. Boom, that's going to be 5 little half-lives. Okay, now we know that the half-life, we're told, is 4 seconds of radon 219. 1, 2, 3, 4. That's it. So what is that time taking? We do a 5, we times it by a 4. Boom. So in total, that gives us 20 seconds, and that's going to be the half-life. Okay, that brings us to the end of this question, and it's been half an hour quick run through of some predicted questions from the physics AQA GCSE higher predicted papers. And that was just 3 questions, and there's 3 sets of predicted papers, so there's loads more if you want to have a go at them. And they're a good way to just consolidate everything that you have been learning. Okay, how was that for everybody? Let me get back onto, I'll stop sharing my screen and get back to the old YouTube. How was that lesson for everybody? Is everyone feeling a bit de-stressed? Hopefully, if like there's still a bit of time before the physics exam. So if anything came up there that was a little bit, anything that came up was a little bit scary, you have a bit of time to go over it. So maybe read over your notes for radioactive decay, click through one of the Seneca modules, do what you got to do. As always, we want these to be as good and as useful as possible. So please give us some feedback. Let us know what you thought. Let us know what you want to see. And we'll do our best to make these as useful as possible for you guys. We've got a bunch of these coming up for the exams next week, so make sure you tune in. Richard won't just be making cameos; he'll be doing one for I think it's for GCSE maths. So if you're getting sick of me, don't worry. There are other Seneca superstars coming your way. But let us know what else you want to cover. Make sure you hit subscribe so you know when all of these videos are coming up. And best of luck with all of your studies. Remember to keep active, keep healthy, and remember it's all going to be over soon. As ever, thank you so much for joining in. And I will see you on the next Seneca stream. Good luck with the rest of your studies and any exams you've got coming up tomorrow over the next few days. See you later. Bye-bye.